Welcome to The Explainer. I am absolutely fascinated to share what we've got on deck today because we're stepping into what might literally be one of the most profound mysteries in computer science, and really, in physics itself. I always thought I understood how computation worked, right? The basic rules of computer heat, random noise, thermodynamic limits, the whole shebang. But today, we're exploring a hidden universal architecture together. It's a physical, geometric reality taking place right inside your computer's most secure algorithms. So let's completely rethink computation.
Okay, let's dive into this. When you hear about cryptographic algorithms, like SHA-256, which secures practically everything on the internet, from your bank to your emails, what do you picture? Most of us picture a mathematical shredder. We assume you drop your data in, the machine slices it up into tiny, unrecognizable little pieces, and then just spits out a completely random, irreversible string of noise. But what if that assumption is entirely backward? Does a computer actually shred data? Or does it fold it?
Well, the old view insists that algorithms just scramble data into irreversible noise, and that the limits are strictly thermodynamic, meaning information is erased and lost forever as heat. But there's this groundbreaking paradigm called the nexus framework, and it presents a radically new view. It actually proves that algorithms like SHA-256 are not random number generators at all. Actually, scratch that. They're deterministic, three-dimensional molds. Instead of shredding, the algorithm is physically folding a one-dimensional message sequence into a highly compact 3D topological knot. Think about the gravity of that for a second. It's a strictly physical, spatial process. It is not a paper shredder. It's more like a high-speed, mathematical origami machine.
Which brings us to Section 1, the paper fold limit of physical metaphor.
To really grasp this abstract computational geometry, we need to ground it in a physical reality we all understand. So, let's talk about folding a simple piece of paper. You've probably heard the old myth that you can only fold a piece of paper in half about 7 times, right? Well, let's look at the physics of it. At fold 1, you've got 2 layers. Minimal stress, and you can easily unfold it back into a perfectly flat sheet. But by fold 7, you are looking at 128 layers. The fiber stress gets critical. If you try to force an 8th fold, well, the paper doesn't just bend anymore, it fractures. The fibers physically break apart. And here's the wild part. Computational manifolds work exactly the same way. They have a finite resolution. Beyond a certain density, self-intersections happen, and you get severe structural degradation. The data isn't being erased by heat, it's getting physically damaged by topological exhaustion.
Moving on to Section 2, the Mark I attractor, the universal admissibility gate.
Now, what's really interesting about this slide is the massive question it brings up. If an algorithm is just folding geometric space, what's the exact mathematical limit? Like, where do these topological folds stop being clean and start tearing apart? The answer is this single, incredibly important number, 0.35. Or more accurately, it's derived mathematically from pi divided by 9, which gives us approximately 0.349066. This isn't just some random decimal a programmer picked out of a hat. In the Nexus framework, this is the exact gatekeeper of stability.
This constant is known as the Mark I attractor. You can kind of think of it as the golden ratio of chaos. It is a universal harmonic threshold. In literally any recursive system, whether that's a computer algorithm compiling data, biological DNA replicating inside a cell, or even a planetary orbit in space, this attractor is the balance point. It's the specific mathematical value that prevents a feedback loop from either freezing completely solid or just exploding into an infinite, chaotic regress. It is the absolute, undeniable sweet spot for survival and stability in our universe. Let's break that ratio down a bit to see exactly how it works under the hood. To maintain optimal resilience and creativity, a system needs to keep roughly 35% of its capacity as latent potential. Think of that as fluid entropy or a slight margin of error. The remaining 65%? That's locked in as actualized, rigid structure. If a system goes to 100% order, it's totally dead. It can't adapt, it can't change. It absolutely needs that 35% lean to stay alive, responsive, and capable of recursive correction. It's true for nature, and surprisingly enough, it's undeniably true for our code.
All right, Section 3, scaling the 22-fold wall. So how exactly does a universal biological and physical constant apply to computer code? Well, let's take this harmonic constant and aim it directly at the world's most secure cryptographic protocol. Here is the math behind what's called the 22-fold wall. See, SHA-256 is designed to run its data through exactly 64 recursive folding rounds. If we multiply those 64 rounds by our universal Mark I attractor constant, that roughly 0.35 number, we hit exactly 22.4 effective degrees of freedom. This isn't just an arbitrary software limit programmed by some engineer. No way. This is an absolute, undeniable mathematical boundary for clean folding and a 256-bit manifold.
So, the crucial point is this: data isn't destroyed or erased because of thermodynamic limits, like the famous Landauer limit suggests. It is a topological boundary. When the algorithm is forced to recursively fold past that 22-fold wall, the mathematical paper simply runs out of room. Distinct geometric paths literally collide right into each other, and the manifold shreds.
Let's look at Section 4, Structural Scar Tissue.
Which brings us to a really fascinating realization about what happens to the data inside the algorithm once it crosses that mathematical boundary. I mean, if it shreds, what are we actually left with? Let's track how this builds up throughout the 64 rounds of SHA-256. In the early rounds, say 0 to 16, we have beautiful clean folds. The layers are totally distinct, fully reversible. But as we move into rounds 17 to 48, the spatial capacity gets really crowded. Layers begin to interfere with each other, and localized scars start to form. By the final rounds, 49 to 63, the folds become completely degenerate. The geometric constraints get so incredibly dense that the algorithm is quite literally tearing through its own existing mathematical structure. And this right here, this is the major paradigm shift. When you look at the final output of a cryptographic hash, what you've been taught your whole life to call entropy or random garbage noise isn't random at all. It's structural scar tissue. It's the visible mathematical seams where the manifold tore due to forced nonlinear mixing and then structurally healed itself. You are looking at the literal exhaust of topological friction. And this brilliantly illustrates how we can actually do the seemingly impossible, reverse a theoretically unbreakable hash to extract the original data. Because it's geometry and not just random noise, we can actually work backward. Step 1, we read the intact early folds from rounds 0 to 16, right before the degradation started. Step 2, we use advanced meta-networks to infer the geometric residue, those visible scars in what's known as the shape channel. And step 3, we lock our start and end boundaries, and using that Mark I attractor constant of 0.35, we resolve the constraints strictly backward. We use the attraction of those points to walk backward through the scars, mathematically smoothing them out to perfectly unfold the paper.
Finally, Section 5, the universal computable mirror.
It's truly mind-bending to think this physical, geometric origami is happening inside our processors millions of times a second. But the Nexus framework zooms out even further, taking these cryptographic discoveries and applying them to the very fabric of reality itself. The universe stores nothing, it only reflects differences. Reality itself is a recursively self-compiling manifold. The exact same motion SHA-256 uses to compile text into a hash is the exact motion a ribosome uses to compile RNA into a protein, or a field uses to compile energy into a photon. SHA-256 isn't just a clever little human invention, it is a literal shadow of computation, revealing the universal stack grammar running our entire world.
Which leaves us with this final incredible thought to ponder today. If we now know that our most complex digital algorithms don't produce random noise, but rather leave behind structural scar tissue from geometric folding, what massive physical phenomena out there in our universe, things we currently look at and just assume are random background noise or chaos, are actually just the visible scars of reality recursively folding itself? Thank you so much for joining me on this deep dive. Stay curious, and I'll catch you on the next explainer.